Hey guys, welcome back to another episode of Simulio. Sorry for the late start today. I was, well, I woke up late. I'm not even gonna try to make up an excuse there. It was, I don't know, last night I just couldn't sleep, and then I woke up, I don't know, at right at, my clock actually said 5:05, but I set my clock 5 minutes early, so I woke up at 4:55, which is, ridiculously late for me. Lately, I've been getting up at 4:30, and I've just been sitting there and thinking to myself, man, I should sleep for another 5 minutes before getting up. But nope, not today. I was totally late getting up. Sorry about that, guys. Okay, so what are we doing today? Well, we're going to continue working on the Huffman forest idea. This is actually a really cool idea, but let me first, real quickly, oh, shoot, go to my Twitter account, because let me see what people voted on for the next YouTube video. So it looks like it's split between Huffman Forests and Monte Carlo. If you're interested in participating in the vote, it's still live, so you can feel free to vote now. It's based on, or it's going to be about what we're going to do for the next YouTube video. So I think, let me see. So if it's split between Huffman Forest and Monte Carlo, both are pretty cool. The way I'll do it is Monte Carlo is probably the easiest of the three to do. I will probably, sorry for that. Hey, we're talking time. I will probably, I like molecular dynamics. It's kind of one of those things. So if we cannot finish the Huffman Forest idea, I will do the Monte Carlo one as kind of a backup. And then we'll do the Huffman Forest the next day, because I've got a feeling after yesterday that the Huffman Forest idea will actually take a little bit longer than I thought. But that's okay. If it takes too long, it takes too long. Not worried about it at all. Okay, so back to the stream. Oops. Okay, so let's open up Zernal and let's go ahead and get started. Okay, so what are we going to do? Let's go ahead and start with a quick analytical discussion of Huffman's algorithm. Hey, Gustorn. And everyone else. So, what are we going to do? Let's talk about Huffman's algorithm. Rhythm. Okay. So, what are we going to do? Well, let's start with, let's pretend you're on the phone. Some guy's giving you a random list of characters. And the random list of characters is I don't know, A, B, C, A, B. Sure, that's a random list of characters. So you have A, B, and C, and you're going to get A with a frequency of 50%, so 0.5. You're going to get B with a frequency of, is this the same string I used yesterday? I don't know. Anyway, I went ahead and implemented a non-adaptive version of yesterday to refresh my memory. It's pretty cool. Yeah, so we're almost done with that one, actually. I don't think it's going to take too much longer. The adaptive stuff, I've been reading the paper by Vitter, actually. He's the one who originally did the, well, I guess Vitter algorithm, and it's actually really cool. Hopefully, hopefully I can get it done, but for the first iteration of the YouTube video, we don't really need the adaptive version. I think the non-adaptive version will be just fine. Okay, so B's are given at a frequency of, 0.33, and C's are given with a frequency of 0.17. I don't know why I put a 0 there when I didn't put a 0 on anything else. So, 17. Okay, so Huffman's algorithm is pretty easy. You take the lowest two and you add them together. After doing that, you get 0.5. Then you take the next lowest two and you add them together. You get 1. You then say one branch has a 1, the next branch has a 0. 1, 0. Then all you need to do is go back and decode everything, or encode everything. So A will be 1, B will be 0, 1, and C will be 0, 0. Now, there's a few things to note about this code that I did note yesterday, but I feel I'll just brief side mentions today. First of all, note that in this code, A is not a prefix in any of these guys. By that I mean A starts with 1, B and C start with 0, so that as you're decoding, you will never at any given point in time assume, as you're reading, be confused as to whether you need to decode A or decode B. It's a non-ambiguous code this way. There's a whole bunch of words that I can use here to mean a whole bunch of the same things, but basically the point is, by doing a Huffman algorithm, you're going to get a code that is definitely usable and also definitely efficient for what you need it for. So what we want to do is implement the Huffman's algorithm again, except this time, I'm going to capitalize the H up here, except this time we're doing it in code, and I've never done it in code before, so we're kind of learning about that as we go along. It should be pretty fun. Okay, so what are we going to do with the Huffman's algorithm? Well, we have a whole bunch of things that I want to try. I've got a really cool visualization that I think is going to look pretty dang good once I get it done. But I also have some really cool... Man, I'm super tired. Sorry, I woke up super late. I said that just a second ago. But I've got some good visualizations that I want to try. I also have some ideas for the visualizations of the other guys too. So it's not like I'm at a loss for how to represent like Monte Carlo or molecular dynamics, which are the other two guys on the Twitter forum or Twitter vote or whatever. And of course, it's totally up to you guys. If you guys don't want me to do a video on the Huffman algorithm stuff next, I don't have to, you know? It's one of those things that at this point, I'm basically creating a list of available videos that I have at any given moment in time, and then I just put them up whenever. So right now I've got like 12 or 13 videos that I could literally make at any given moment in time. So just if I'm busy or if we're working on a complicated algorithm on the Twitch stream and I'm not able to get everything done, I just make a video on something simple like, I don't know, Lagrangian mechanics or something like that, Hamiltonians, things that people don't typically think of but are totally important to ask about. So like principle of least action and stuff like that. I don't know, there's a whole bunch of videos that I can make. And basically the idea is that like sometime during the week when I start preparing for the next video, I'm just going to send a poll on Twitter and say, hey, look, these are the ideas. Which one do you want me to do? Anyway, back to the Huffman algorithm. Now, there are some cases where the Huffman algorithm could be considered suboptimal. And let me kind of explain one to you. So if we have an entire string that's maybe 100 characters in long, so I'm going to say char of 100 in length. Okay? Now, let's say at the start of the character, we have A. Then, at the end of the character, we have all the letters of the alphabet somewhere in between, and then we have Z. And that's it. These are the only Z's we have in the entire algorithm. Meaning that actually somehow, Z's are one of the least used bits, right? Based on this encoding scheme, A, well, could be, potentially, the most used letter. And so A could be very short. Z, though, being one of the least used letters, could be very long. And so you could imagine a situation where we have very, very short areas and very, very long areas because we've searched through the entire string first in order to create that frequency that we needed to add together in the last slide. If that doesn't make sense, let me put it to you this way. So page, new page before. Let's say we get a string that is, I don't know, AT, let's say, Bobby, Bubbles, Bubbles, Bibbity, Bibs. Okay, there we go. Bobby, Bubbles, Bibbity, Bibs. Okay, that's what we got. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26 characters total. Okay, so let's go through. B's are the most frequent. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 B's. Next, let's see. O's, U's, I's. I bet you I's are the next most common. I are going to be 1, 2, 3. Next, let's do O's. Do we have to get a 26? Oh, no, I bet you spaces were the next most common. Spaces are the next most common. 1, 2, 3. Oh, never mind. I, 3. Spaces, 3. Okay. Now what's next? Bobbity. O's, T's, and L's. So let's do, I think, S is going to be the next most common with 2. Then we have, what's next? Y's with 2. L with 1. T with 1. I feel like I'm missing something. An E. We have an E. Well, I planned this poorly. Let's see. L with 1. T with 1. E with 1. Let's add these guys together. What do we have? We have 11 plus 3 and 3 gives you 17. Plus 3 gives you 20. This gives you 24. I'm missing a U and an O. Okay, so here's what I'm going to do. I'm going to scroll down a little bit. U1, O1. Okay, so now we have 26. Here's what we got to do. We add these two guys together to get 2. We add these two guys together to get 2. Now we have 1 here and a 2 here. Okay, so we always have to add the 2 lowest, right? So we can add this 1 to just about anything. I'm going to add it to this guy right here. So this is going to be a 3. Okay, so now we have a 2, a 3, a 2, a 3, a 2, and a 2. So let's add these two guys together to get a 4. And then add these two guys together to get a 5. Okay, so now we have 4, 5, 3, 3. Add these two guys together to get a 6. Now we have 4, 5, 6. So let's add these guys together to get a 9. Now let's add these guys together to get a 15. And these guys together to get a 26. Okay, so if we were to draw out what this guy turned into, let's do that. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, so let's draw it out. B, I, space, S, Y, L, T, oh, sorry about that, T, E, U, O. Okay, so B is going to be 1. That one's easy. I is going to be 0, 1, 1. Space is going to be 0, 1, 0. S is going to be 0, 0, 1, 1. Y is going to be 0, 0, 1, 0, 1. Okay, what's the next one? I is going to be, or L is going to be 0, 0, 1, 0, 0. Okay, next it's going to be T. It's going to be 0, 0, 0, 1, 1. Yep. Okay, is that right? 0, 0, 0, 1, 1. Yep. Okay, next one's going to be E, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And then the next one's going to be U, which is going to be 0, 0, 0, 0, 1. 1. Okay. 1, 2, 3, 4, 5. And then the last one's going to be 0, 0, 0, 0, 0. Okay? So one thing to note is the length of this one is 1. Length of these two are 3, 4, and then the length of all of these guys are 5, right? The idea behind Huffman encoding is that you're able to store these bits in a way that is, well, more efficient than the way you were going to store bits before. And in this particular case, if somehow after the bibbidi-bobbidi, Bobby Bubbles Bibbidi Bibs, you get a whole bunch of O's, well, that's super inefficient. Right? So in this particular case, you could imagine that after the encoding, or maybe even during the encoding, because of local fluctuations in a particular variable or a particular letter, it could be that it is inefficient for other local areas, right? And so here's where we bring in the idea of adaptive encoding, and I'm kind of giving you guys, well, putting your toes a little bit in the water or whatever for the next simulation that we're going to do. But for now, we've got plenty of time. Let's go ahead and go through and work on the Huffman algorithm as it currently stands, which is what we just implemented down here. And then we'll worry about adaptive methods next. With the YouTube video that I'm going to be doing next, the way I see it is I'm going to do a standard Huffman algorithm, and then we'll do adaptive Huffman algorithm at some point later. I'm probably going to put a to be continued at the end of my next Huffman algorithm thing. The whole thing about classical Huffman encoding is that It needs perfect information. Yeah, that's totally true. The idea is that you have a perfect frequency, or not perfect, but you have a frequency that you know 100% is accurate coming into the situation, right? And so this kind of idea, this type of encoding that I just did, is maybe a little disingenuous towards Huffman encoding in general. Okay, so I think at this point in time, guys, we can go ahead and start working on the code one more time. And I'll admit, it's a little rough because I've never done this numerically before. But that's okay. You know, I need to get it done soon enough. So we're going to pop this over there, and let's cd into projects, Simuleos, and of course, Huffman. What did I call it? Lowercase h. Come on, it's a guy's name. Why did I lowercase the h? Projects, Simuleos, Huffman. Okay. Now, let me go ahead and get a quick sip of water, and then we'll get started in just a second. I woke up late, so I wasn't able to refill my water. So at some point, I'm gonna get like super thirsty in the middle of this, in the middle of today. Okay. I also turned on the air conditioning. If you guys can hear any type of buzzing or anything like that, let me know, but I think it should be fine. Okay, Huffman. What are we going to do with Huffman? Let's go ahead and look at what we've got. We've got a couple of different things here. I was checking the bitset stuff yesterday. So let's go ahead and open up Huffman.cpp. Huffman.cpp. Okay, so yesterday, what did we write? We only wrote one thing, and that was the create nodes function. Now, there's plenty of ways to write this, and I'm looking around for my lab notebook. Ah, found it. 1 second. I needed a paper I was reading last night, just to make sure I don't accidentally do something stupid. But again, the Huffman algorithm is not, in essence, a difficult thing to do, right? And we're going to be implementing it in kind of a stupid way right now, but once we move on to the Vidder algorithm, it becomes more challenging. So keep that in mind. The first implementation is probably going to be a little bit simplistic, just because we want to get it out there, because it could potentially be used soon enough. Okay, so what do we have to do next? Well, we have a couple of different guys here. So we have one that will create, let me see, what do I have here? We have one that creates all the nodes, and let's go ahead and run a.out over here. It looks to me like all we have to do is SDC out initial nodes, keys, and weights. Okay, so each node has, let me see up here, a node to the left, a node to the right, and a parent. I should probably actually, now this is probably worthwhile to do it this way. Okay, that's fine. Now, obviously, if you're in the right node, your left node is null, and if you're in the left node, your right node is null. That's kind of how it is, but that's okay. Okay, so now we have to actually write the Huffman algorithm, and we just did it analytically, so hopefully we can get this done numerically pretty easily. Now, guys, I have to point something out. I've been in the habit of calling what we do here numerical physics, and I want to point out that this right here is not actually physics, but when I say numerical work, I mean work on computers. A lot of people, I think, get numerical physics and computational physics confused. And that's because numerical physics isn't actually a thing. It's just you do numerics in theory, right? Computational physics, I used to say that we're like, that this channel is the only one that does computational physics on Twitch, and that's totally true. We did for a while do that. But this kind of stuff right here, when we're just testing out other algorithms, I feel like this isn't computational. I feel like it's numerical. It's just my own personal preference. The difference is just that computational is usually done on supercomputing clusters at some point at some location for some, crazy reason. I don't know. It's usually with parallelization, and it's usually more programming than it is theory. Numerics, I usually say, is more theory than it is programming. So this is definitely more theory. Here's the thing, you'll either want to pass SDE vector by reference and modify it in place, or generate SDE vector node. Yeah, let me think. We'll kind of work on this. So the next one, SDE vector, yeah, so I want to pass it by reference. Here. Okay, what do I have here? Vector node, SDE Huffman, initial nodes. Let me think. So wait, you'll either want to pass SV vector node by reference and modify it in place, or generate an STD. Otherwise, you'll set left-right parent nodes to memory that will be freed. Yeah, you're right. So I'm going to set this actually to void then, and we're just going to update the initial nodes. And let's go up here and go down there to void. Okay, let's go here and add in this guy. Okay, so now how do we actually do the Huffman algorithm? Well, since we've got a vector of nodes here, let's just kind of go through and work on it. So first things first, we have k leaves or k nodes to start with. And basically the first thing we need to do is sort everything based on their weight, right? You could return a node as the root. I don't know exactly what you mean by that. So if we have all these nodes that are all of the different, how do you say, all the leaves on the edge of the tree, right? And we're going to be combining them into nodes. Then you could return a node as a root. Create a new node P. Okay, so here's what I was planning on doing. Yeah, I just don't know what you mean. Oh, you want, in the end, you want me to return just a single node, which is the root. Okay, I see what you're saying. Let me think. If we return just the root, would we be able to reconstruct the entire tree? I feel like I would like... Let me think. So if we return the root, yeah, I guess you're right. We could. Yeah, you're totally right. That's actually kind of interesting. Let me try that. So let's read in a vector of initial nodes, and let's output just the node. Because it's going to link to your left, right, and parent node. You could actually just return... the idea here is that we just return the root node, and then you actually rebuild the tree every time, which is actually really cool. So let's go through and try that. So what are we going to do? We want to do, instead of void Huffman, let's change this to node Huffman. And actually, guys, I'm going to have to leave this a vector node that we change by reference. And the reason for that is because I'm going to have to add in some new nodes and manipulate the nodes that we add together. So the very first thing we need to do is sort everything. So let me go down here, and let's do, first thing we need to do is sort the vector by, what is it going to be? The weight. Okay. And this is going to have to be done a couple of different times. So here's how I'm going to do it. I'm going to say while, let me see. Let's also create, how do I put this? I need a length too. You still want to take the vectors by reference or have node stars. I thought I did take the vectors by reference. Yeah. So I mean, I am sending the nodes in by reference. So I think, or at least I feel like this should be okay. But we'll see how it goes. Again, I'm not so great with pointers. I know I should be better, but I'm just really bad with pointers. Node stars. Well, we got to modify the initial nodes anyway in this particular simulation. But yeah, could we not do both? I mean, what's wrong with doing both? Vector of node stars. Let me think. So in a vector of node stars, what does that mean? That means the node itself is, I guess it's fine to just be a pointer then. There. And let's go up here. Vector of node star. Okay. Let's go down here. Now, we're going to have, oh my gosh. We're going to have to define a total length. And let me think. How are we going to generate a total length? At this point, I can't think of the best way to do it. In the algorithm that, I'm used to, it says while the total length is at least 2 nodes. So we have 2 nodes left. We haven't combined everything yet. We're fine. Now what we could do is we could create a separate vector every single iteration that is the number of nodes left over. And that's perfectly fine. However, for me, I feel like that's a little bit inefficient. The easier way for me is just to create a simple flag that when flipped, it means that we have completed, or we have found the root node, right? So basically we keep going until the root node is found. So let me think. Or, let me think. I guess at every given moment in time, let me see, how are we going to do this? That means that each node will be head allocated, head to heap. Okay, I think I get it. Okay, so here's what I'm going to do. I'm actually going to, because I just realized we actually need all of the weights anyway. How do I actually want to do this? We need a list of initial nodes, and then we also need a list of current nodes. And I think what I'm going to do is I'm going to have a list of current nodes. Oh, it won't work as it is? Oh, okay. So I guess I don't understand it well enough. Let's go up here. Let me see. You said... I need another drink of water. Okay, I appreciate that. Sorry about that. Okay, so here's what I'm going to do. I'm going to create root flag. Int, or let's say boolean root flag equals false. I don't know if I can do it this way, so let me write and let me compile it real quick. Yes, I figured that wasn't true. Let me see. False with a lowercase f. Okay, that one worked. And then we say while. And let's do root flag equals false. We continue. So this is saying while we do not have root, we continue. Now we can find a more efficient way to do this in a second. For now, I'm just going to do it this way. Root flag is flipped when we have, how do I say? When we have, root flag is flipped when we have found root. Okay, let's go down here. Wow, root flag is equal to false. We continue. Okay, so now the actual algorithm. And here's the thing. I'm going to have to create a list of current nodes and also a list of initial nodes to work with. So every time I remove a node from the current nodes, in order to, let me think. Yeah, I'm going to have to add nodes to the initial node list. So let me see if I can do this. What I'm going to do is create a list of current nodes. Work with. Okay, now we're going to say current nodes. We're going to say vector of node is going to be equal to current nodes. Node. Okay. Now, what's the next? We now need to go through, and what we can do here, instead of doing the root flag stuff, is we can go and we can say that, what do we want? If you use a priority queue, I don't know how to use a priority queue because I've never used that before. Okay, so we're gonna say current nodes dot size is greater than 1. You can do the whole thing by using a single priority queue. Again, I don't even know what a priority queue is, so that doesn't help. Q C++. Okay, let me see. Priority queue. A priority queue is a container adapter that provides constant time lookup of the largest by default element at expense of a logarithmic insertion and extraction. A user-provided compare can be supplied to change the ordering. SKey greater would cause the smallest element to appear at the top. Let me see. Working with a priority queue is similar to managing a heap in some random access container, with the benefit of not being able to accidentally invalidate the heap. Let me see, what do we have? So if I want to find SE priority queue int q for int n in all of those numbers, we say q push n, print priority queue, or print q. Okay, SD priority queue int SD vector int SD greater int q2. So what's the next one? So it says for int n to q2 push n. Okay, and then print q. So what just happened? It is now from smallest to greater than. So let me see, what did they do? They did SD priority queue. Yeah, so it looks to me like that's exactly what it does. Yeah, so this would mean that we don't need a sort function. We could just use a priority queue. So let me implement a very simple case of this, and let's see if we can, let me see. So it looks like priority queue of int, SD vector of int, SD greater of int. Okay, so it's just something that we add in. Let's see, it comes with a queue. Okay. So we have a vector. No, we don't have any vectors here. It's just all of them are priority queues instead of vectors. Okay, so let's try that then. Basically, I think what we'd have to do is change all the vectors to priority queues. And then we can continue from there. So all the vector nodes will be changed to priority queue nodes. So let's go to S. And let me think. Yeah. Good. Okay, so now let me think. What else do we need to do? I need a custom comparer? Why? Why can't I just use the weights? Oh, 1 second. Okay. The other thing. I'm sorry. Okay. Let me think. So, what am I going to do? I'm going to change all the vectors. So let's do std vector to, and let's look up node to std priority queue. Is it spelled like that? Yep. Of node. Okay, and then we call the priority queue. That should be fine. Okay, so now they should all be fixed, or changed rather. Let's go ahead and run this and see if it runs. It does compile. So now let's go down here and let's see what we got. So we need to sort everything. This needs to be std priority queue node. Queue. Okay, so we have the list of current nodes still. Okay, let me see. Open link. What do we have? It looks like struct node compare Boolean operator constant node left, constant node right, constant return left weight greater than right queue. Okay, wait a minute. Boolean operator constant node left, constant node right. That's fine. Constant return. Why are we comparing left and right? I'm not actually sure why we'd... Wait, why are we comparing... I thought we were just going to sort everything. That's fine, but I guess I'm not... I'm kind of confused as to why we are comparing just left and right instead of comparing the entire priority queue. You know what I mean? Like, I would have thought that we would have gone through... Refresh. I guess I'm not understanding. So here's the idea. If we're comparing left and right, let me think. SD priority queue node, nodes compare. Okay. So why are we comparing Boolean operator constant node left, constant node right, constant return left, right. You can always sort any collection by knowing how to compare two of its elements. let me see. That's probably fair enough. So we're going to be at an individual node. We're going to say return left weight less than right weight. I mean, that's fair enough if we already have the head, or if we already have the root. But if we don't already have the root, and these guys have no lefts and rights yet, I'm not sure if this will work out. Yeah, I don't know. Okay, so let's go here. We do priority queue of node, current nodes. Okay. Just at the start, once we have, kind of a... Oh, okay, I see what you're saying. You just want to compare... Do we read in the left and right? Let me see. How does this relate to this guy up here? Because here they have void print q. Let me see. That's not what I want. In sd vector, sd greater int. Why can't we just do sd greater? Oh, okay. Maybe because we don't have ints. We have nodes. Okay, I see what you're saying. Yeah, that's fair enough. Okay, so let me see if we can do this. So what we need to do... Okay, so struct node compare. Okay, let's see what happens if we mess around a little bit. So let me go up to the top. And let me go here and say struct to compare nodes. Okay, so we're going to say struct node compare, similar to the notation that Gustorn has given us. Okay, we're going to need a semicolon at the end here. Now, what do we need to do? We need to... let me see. Now, what does this Boolean operator do? So the operator... Okay. Okay, so we're going to say Boolean operator. Oh, sorry about that. And it's going to return a true or false. And we want constant node left and constant node right. Okay. Then we say constant, and then we read in the following. Let me see. Struct node compare. Wait, do we have an extra squiggly bracket? No. Okay, that's fine. I was just being stupid. Okay, so let's go here and let's do return left dot weight less than right dot weight. Okay. So what we need to read in then, let me think. So if we do this operator, so imagine it this way: when you insert into a priority queue, you have a new element. The priority queue will call that function with the arguments. New element in queue element. Whenever it first returns false, it will insert the new element into the queue. Okay, so if we say, so we're reading in two nodes and we're checking which one's greater than the other based on the weight. Yeah, that's fine. Yeah. Okay, so I think this kind of makes sense. And we're basically going through the queue and separating it all, or putting it all together. So does that mean when we initially create the queue with the weights, let's see. We do node Huffman here. And then what do we do? When we initially create the... Oh, well, that's not right. Oh, those are vector characters and doubles. That's fine. So when we create the initial nodes, here, priority queue, we say, let me see, what did I call it? We called it node compare. Here. Would this automatically... Okay. See what happens if we go here and write that. I think, yeah. So I guess this would mean whenever we insert a node, we insert it with this guy in mind. So let's see. Let's add in a third weight, and we're gonna do 1, 2, 1. 1, 2. So we're gonna do 1, 2, 1, 3 actually. And then we're gonna go up here. We're gonna say A, B, C, and D. Okay, let me see what happens if we write. Sorry about that. We go over here. We go to G++. Okay. Let's see what's wrong. Error. Priority queue node is not a member of STD. That is because I didn't read it in. QUEUE. Let's go over here to G++ Huffman. And let's see. No match for operator. In place back in place. Okay. G++. Let me see. Let's go ahead and clear so I can see it a little bit easier. And let's do G++. Okay, so it says no match for operator. Let me see. How do we pull an initial element out of a priority queue? Because apparently it's not the same as a vector. Expected unqualified ID before... Oh, that's fair enough. Let's go to 96. Priority queue current nodes equals initial nodes. Okay, so now what else do we have? Current nodes not declared in the scope. That's fair enough. Okay, so those two are fixed. Now for the top one up here. Let's see. Reserve initial nodes is a non-type. Okay. Keys.size. Priority queue node. Let's go to 82. Initial nodes dot reserve keys.size. Okay, so I guess maybe with priority queues. Yeah. Okay. Okay. What's next? In place. Let me see. Request from member in place. Let's go ahead and clear this one more time. And now let's go to G++ Huffman. Oh, I forgot to write. Clear, G++ Huffman. Okay, so we've got a few errors here. No match for operator. That's fair enough. That's fair enough. In function, priority queue, create nodes, vector, character, STD vector double. Request for in place in initial nodes, which is of a non-class type. Okay, could not convert initial nodes from STD priority queue to STD priority queue of node. Oh no, that's interesting. Okay, so let's go to 89. Okay, so when we return the initial nodes, apparently the priority queue up here is defined with the node compare in mind. So let's see, where do we define it? We define it with that node compare. Let me see. How am I going to... I'm gonna have to mess around a little bit. Let me ls. I have a test function here. ls. There we go. Let's go into bitset check.cbp. Let's go here and add in q. Okay. Let's go down here and let's check some q stuff. Checking q. One second, let me check my stream real quick. Yeah, okay. Good. I thought because I have this weird thing right here that maybe the chat was down. So we're going to do, let's go ahead and create a priority queue. And let's see what we got here. So we'll say std priority queue. Okay. And it's going to be of integers. And it's going to be called priority check. Priority check. Okay. Now, what we did before, let me see. Priority queue. And then what do they say? They say priority queue. Okay, so what we need then, okay. Priority queue nodes, node compare, that's fair enough. Using node queue equals SD priority queue node, SD vector node, node compare, node queue generate. It's using a lot of words there. So using node queue. Okay, so that's like using, okay. So we're defining node queue as SD priority queue node. Okay, that's fair enough. Then we say node queue generate. What does generate do with priority queues? Let's do C++. Okay, priority queue, create, let's see, what do we have here? Using as a type def. Yeah, I definitely have. Okay, so what does the generate guide do? That's the thing I don't know. 1 second. Does not produce any outputs. Priority queues are type container adapters. That's fine. We look for generate. No. Let's just do generate C++. Okay. So generate values for range with that function. Oh. Sorry about that, guys. Okay. That's fine then. Let's go over here. That means, let me see. The idea then is SD priority queue nodes, and then we say node queue. Okay. So the idea then is that we are, yeah, so this needs to go up here. Oh, sorry about that. And generate is the function we're using. So what we need to do then is SD vector, no, yes. So we want, instead of SD priority queue, what we want is node queue. So let's go up here. And let's go to here and say using node queue as, what are we saying? Equal to std priority queue. And then what do we want? We want to call in a couple different guys. So node, std vector node, and then of course the last one, which is the one I had trouble with and I don't remember. Shoot, node compare. Okay, SD priority queue node. There. You have to place it, the using below. Yeah, I just realized that right now, because otherwise it doesn't know what I'm talking about. So let's go down here. And let's go here. Okay, so now what we can do is erase this guy and say node queue. Let's go up here. And let's do std vector double weights. Okay, dd this guy. And now we go down to the create nodes function. Next. Let's change this instead of priority queue. Let's change this to node queue. Okay. So what are we going to do? Priority queue, this one, node queue. Move this guy down here and add in this guy there. Let me see. In Huffman. Yes, I should. Let me go here. Sorry about that, guys. Node QUEUE. Initial nodes. Okay, this should be fine. Maybe there's something else that I forgot, but that's okay. We'll hit it as we hit it. So let's go here. Node Q. Okay. Now, what do we need to do next? I'm not going to check this anymore because I think I kind of sort of, in a way, get it. G++ Huffman. Okay, what do we have? So the square brackets don't work with the priority queue. So how do we pull elements out of a priority queue? C++. Let me see. So we have for int n is 1, 2. We're going through all of the priority queue. So it seems to me like this should work. We have to pop out the particular element. Okay. So that means what do we need? For line 72. Let's fix it once and see if that fixes it. Initial nodes pop I guess. Pop I dot key. Let's do G++ Huffman. 72. Of course not, because I missed G++. And it looks to me like no matching function call for SD priority queue dot pop. Okay, how do we pull individual elements in priority queue? C++. Let me see. Insert elements, priority queue. You actually just pop the top element? 1 second, let me think. Oh, first of all, this is wrong. No, that's right. I'm not sure I understand what's happening. So why would I don't know. I have no idea what's happening here. I should have just done a sort, because I get that. Okay, so let me see. I don't understand. What? Okay, I'm gonna have to test this. So let me go here to bitset check, priority check. That's fine. Now let's go over here to, what is this? Generate. No, this is what I want. That's not what I want. This is what I want. Okay, so what do we have here? A priority queue Q. So let's set this to be here. std vector int, and then we have one last guy, which is std greater int. Yeah, but at least I understand it. So let's go here, priority check. Okay, so we have our priority check here. So now what we want to do is push all of these guys back. So we're going to say for auto I in, what is it? Auto int n in the following guys. So we're going to say 1, 2, 3, 4, 5. You can actually do it with 2 vectors without sorting, but it would seem like you're going. No, I was just going to sort every time. It's super easy. It's not efficient, but who cares? So let's go to 3, 2, 1. Okay. Now we're going to say, let's go here, and we're going to say priority check dot push. And what do we want to push? We want to push I. Okay. Now we want to, how am I going to see out this? That's the thing I don't understand. So I have to go through all the elements. Yeah, it's just a nasty way to do it. How do I get an I? I just want an I element that goes through each one of these guys. Well, let me see if this compiles, and then we'll go from there. So let's do G++. Oh, I'm sorry, G++. Bitset check.cpp. I was not declared in the scope via bitset check. Let me see. That's because I said int n. Okay, let's go through here and change this to an I. Let me see. You don't random access queues. You can actually do it with 2 vectors with only 1 sort. You don't random access queues. I don't know what they're for. I thought they were just vectors. Okay, so we're gonna push I. Let's do G++. Okay, now we're gonna go bit set check. I mean, that's fine, but I need to find a way to print it out in the end, and the only way I know how to do that now is by doing this, and I don't like doing this. For int I in priority check. Let me see. Let me see. I don't even know if I can do that. Priority for int n. Let me see at q top. Oh, we need to do q pop. Wait. Does q pop remove the element from the system? Okay, so let's do priority check. STD. What am I doing? For let's see, int I equals 0, I less than priority check dot size plus I. Okay. So now let's do std cout priority check dot size or pop top. Okay, end line, and then we want to do std cout priority check dot pop. Let me go here, right quit, and let's do G++ bit set. Of course it breaks. Okay. No match for operator. No match for operator. Okay. But I didn't use pop, I did top. Oh, what? I did top. Okay, let's go down here. Yeah, I did top. Oh, that's because I did cout. Sorry about that. I meant to do just priority check. Dot pop. Yeah, that's what I meant to do. Okay, so that outputs 1, 2, 3. It's not even in the right order. Okay. Why is it not in the right order? Okay, let me see. That's what I meant to do, Gustorn. Okay, so now I have to figure out why it's not in the right order. So, int n, pushback n. Yeah, we're doing the same thing they're doing. Let's see, we defined it as greater. Let me see. Declare type CMP, I don't know what that means. Int vector. Do I? Well, then that still doesn't make sense, because if we run it, we do a.out, it only goes 0, 1, 2, 3. Where's 4 and 5? That's my question. So if we go to bit set. Okay, so we're going through all of these elements, 4, 3, 2, 1, and 5. We're pushing them back. We should see 1, 2, 3, 4, 5, right? For I equals 0. Let me see. Priority check pushback I. So we're going I through 1, 2, 3, 4, 5. Actually, this doesn't even make... Okay, so we're getting 1, 2, 3. So we're missing 4 and 5. Okay. So let's see if instead of going through priority check.size, we go through, looks like 5. Or, yeah, 5. G++, a.out. Yeah, that one works. You have to do int size before the loop. Oh, I see what you're saying, because we're popping them out. So yeah, that's fair enough. Yeah, you're right. I wasn't thinking about that. So we're going to do int size. Sorry about that. Size is going to be equal to, what do we want? Priority check. Dot size. Okay, and then we go through here, we do through size. Okay, that's fine. Let's go ahead and write and quit. Do quick g++, a dot out. Okay, well this is good to know. Thanks again, Gustron. I had never used priority queues before, so this would be interesting. So do create nodes, priority queue, initial nodes, compare. So what I want to do then is up here, I want to output some stuff, and I'm going to, for now, comment out the Huffman stuff down here, just to make sure what we had yesterday was currently working. And then we'll kind of move from there. Write this, go over here, and let's go up to here. Oop. Yeah, you're totally right. I got you there. So we say nodes, let's do, so pop will remove that. Let's do top of key, and then let's do top. Oh, that was not what I meant to do. Top.weight. Okay, let's see how that does. And now we're going to, down here, say initial nodes dot pop. Okay. Right, and now we're going to go over here and we're going to run g++ Huffman.cpp. Okay, initial nodes pop. That's because I misspelled initial. Initial. Right here, g++. What's next? Mplace. Request for a member mplace and initial nodes, which is of non-class type std priority queue node compare mplace keys. 1 second. Request for member mplace and initial nodes. Could not convert initial nodes std priority queue node compare. Return initial nodes. Okay. Let me see. Node queue, create nodes. That should be fine. Initial nodes mplace. So we're having trouble down here with these last couple lines. So let's see. Initial nodes mplace keys weights I. Okay, size t equals 0. I less than keys.size. So we're going through all the keys, and we are adding in all the keys and all of the weights to each of the initial nodes. However, let me see. Request remember mplace and initial nodes. Let me see. Could not convert initial nodes from std priority queue to node queue. Let's see. Return node queue. More initial nodes. So we're returning a node queue. Could not convert. Okay, so it doesn't like. Let me see. That's because up here we need to change this guy to node queue. So that should fix that last bit. Okay. We're going to go over here, run g++. Wait, let me clear a couple times. Now let's go g++. So error could not convert initial nodes. We can probably remove this. G++ Huffman. Okay, so that one works. Let's do a.out. db32. Okay, so that's because we have to do the same thing we did up here. So we're going to say, size, int size is going to be equal to initial nodes dot size. Okay, add in a semicolon, and then we're going to go to size. And then we should see that we output everything. Oh, my bad. As we should. Let's do g++, a.out, 3211. That is correct. Let's see, 3 is the highest. So here's what I want to do. I want the very highest one to be try push. Yeah, no, that was my bad. We had changed so many definitions. I should have kept up, but I didn't. That's okay. We're perfectly fine. So what do we need to do next? What I need to do is change the comparer such that it is greater than. And the reason I want to do that is because, let me do it here. That way least powerful ones are the ones on top. And this is what we need for the Huffman algorithm anyway. So we need to take the two, okay, I see what we're doing. So we're gonna take the two lowest, so 1 and 2. So we're gonna pop the first 2, and then we're gonna send it into a new guy. That's exactly what we're doing, and this makes sense. Good. We're getting there. Just again, I'd never used a priority queue before. It's perfect for this case. I do agree now that I see what it does, but took me a while to get on board. Okay, so now we have to do the Huffman guy. And what do we want to return? We want to return just the highest node. However, the more I think about this, the more I kind of feel like, let me think. Oh, you send it back to the same queue. Really? Oh, actually that's fair enough. Yeah, because we're going to have to add them all together. Okay. But now my question is, when we reconstruct the tree, and this is something I'm not sure I fully understand, but if we're sending them back to the same queue, that means we don't keep the nodes. When you only have one remaining, you have the root. Let me think. So with the root node, we will have a left and right. No parent, but we will have a left and right. Okay? So we'll have a left and right node, but those left and right nodes don't exist, right? So how do we recreate a tree if those nodes don't exist? Let me think. Let's see, so the node itself is going to be I need the nodes. I'm just trying to think here. So, here's the situation we got. Let's do a page, new page before. When you only have one remaining, you have root, and that's why you should use node stars. Okay. So let me think. How am I going to do this? So we have a situation where we have like, let's say 5 different nodes. So we have 0.5, 0.3, 0.2, 0. What do I have left? Oh, I have nothing left, so 1, 1. Okay, so we have these nodes. They're set in such a way that we can very easily add these guys together, then add these guys together, then add these guys together, and we can get our appropriate guy back. Now, what we need to do is return back a, what I'm going to say is what we need to return back is a sorted, vector of all of the nodes. I still think we need a vector of all the nodes. So here what we're going to do is we're going to say 0, 1, 0, 1, 0, 1, 0. And if we have a vector of all the nodes, then I think we should be fine. So they're all held in some sort of data thing. And then this makes it kind of easy. You don't need the vector? Why don't I need the vector? So you're just saying do node star and keep it as some sort of array? Okay, let me think. I guess that's fine because we're pointing, right? So we'd have a node star which points to here and there and there. That's really tricky, so I'm going to try it and I'm going to fail, but let's do it. So let's see what we got. Okay, so instead of returning a node, we're going to return a node star. Okay, let's see what we got. Node star. Okay, let's go up here and return the node star from Huffman. Okay, so here's what we're going to do. We're going to say node equals new node. Oh, heap allocated data structure. Use node star like node. Use node star like node star equals new node key weight. What are we returning from Huffman? That's my question. I don't understand. Oh, like, okay, I think I see what you're saying. Maybe. So we would return. Oh, that's, why do I, let's see, new C++. This is also something I don't use very often. So let's see, new T. Sorry, Gastorn. Let me see. So what I want to do, void star, operator new. Let me try something real quick. So I'm going to go into the same thing that we were working on before. So vi bitset check.cpp. And let's see, what do I want? I want to do the following. So let's do double star X. Okay. I want to say, how do we use this? Like node equals new node. So I guess it'd be node star equals new node 5. Okay. So we'd set it equal to 5. No, I don't. I have no idea how to use new. Okay, so let's say. So in this way, we're initializing node. What you wrote down is we're initializing node with a key and a weight. Okay, let's go through and let's just do it this way. So we have initial nodes, and that's fine. So since we already have it defined as a priority queue, that should be okay. And basically we go through and we say, while current nodes dot size. So we're going to say initial nodes. Okay. 5. Okay, what do we have? Return x dot weight, y weight. Let me see. It's fine though, right? To use, what's the difference between using dots and arrows in that particular case? Aren't they both basically the same? Let me see. That's okay. Now what do we want? Priority queue node star nodes. Okay, with node compare. Let's see, node queue, that's fine. Node queue generate nodes. Vector, character, keys, character weights, and we basically say nodes push new node, key, and weights, and then we do node Huffman. Dot won't compile. Really? Oh, that's because we have a different operator. So what you have, yeah, okay. You have node star left and node star right. Okay, then we say left pointing to weight and right pointing to weight. Now, when we do all of the priority queues from now on, the priority queues have an additional star. Okay, so I think this guy should be of node here. Let me see. Yeah, all of them have additional stars. So let's do priority queued nodes, node compare. Using node queue. Okay, so let's go here, DD, and let's look for all these guys. So basically what I need to do is every time I see a priority queue, I need to go through and change it. But I think since all of these guys are node queues, it should be okay. So let me look for the next node. Okay, node is there, but that's okay. Node is there, those are all nodes. That is all perfectly okay. Node. This is going to have to be changed later anyway, so let's go here and change this to node queue. Okay. Okay, let me see if I defined it in main. Node queue, node. One thing you'll have to pay attention to is freeing the memory allocated by create nodes. Yeah, I'll have to look into that. I'm not sure if I totally get it yet, so we'll kind of go through and see what we need to do. Okay, so what do we do? We need priority queue node. I think I updated everything. Character keys, generate nodes. Yeah, so I think everything should be fine. Let me see. Yeah. Okay, I think everything's fine there. So let me go ahead and write this. Right quit and run Huffman. Okay, apparently not. So error expected initializer before create nodes. Where is create nodes? Node queue. Oh. I don't know what happened there. Let's do clear. we're gonna do Huffman. Int main, initial nodes, top key. Arrow requested from member key and initial nodes. They probably need to be arrows. Okay, so let's go down here. And let's do arrows. If I can write an arrow. Okay. G++. Okay. This is gonna be... here it is. Included, let me see. New initializer expression treated as components. Let me see. Cannot convert double to node star in initialization. I don't even know where this error is happening. In file allocated. 1 second. This seems to me like it shouldn't. Oh, where's push? Okay, that's fair enough. Create queue nodes in place. Okay, so what we need to do is nodes push. Then we want new node of keys and weights. Let's try G++. Okay, that worked. Thanks, Gusthorn. And that still works. Okay, good. This is still kind of working. Let's go down here and let's see what we need. So, well, initial nodes dot size is greater than 1. Here's what we're going to do. We are going to add the two nodes together and... Okay, let's do this. So add two nodes together and point to the previous nodes. Okay, here's what we need to do then. So we take the two nodes here. So let's see, we need node 1 and node 2, which will be the two of lowest weight, which is what we have currently. So we'll say, how do I want to do this? We'll say, we'll say, node 1, let's see, what do we call it? Node Q, node 1, node 2. Okay. Man, I feel like I'm about to sneeze like every single second. Okay, let's go down here. Let's do node 1 is going to be equal to initial nodes dot top. And then we're going to say node initial nodes dot pop. Then we say node 2. Yep, fair enough. Okay, node 2 is going to be equal to, 1 second, initial nodes dot top, and we do initial nodes dot pop. So we have the two nodes out. Now what do? We need to add them together. So what do? We say, let's go up here and then say node parent. So here's what we're going to do. We're going to say node parent. And what do we want? We want node parent weight to be equal to the previous two weights added together. So node 1 weight plus node 2 weight. Okay. Good. So now we need to, let's see, set these guys up appropriately. So we're going to say, and this is where it's going to get kind of confusing, and I'm not sure exactly how this needs to go. So we're going to say node parent. Let's see, how do I want to do this? We're going to say it should be of the greater of the two. Okay, so this makes sense then. So we're going to say node parent. Let's see, what did we call it? Right? Right is going to be equal to node 1. Wait. Which way do we put this? Doesn't matter. we're going to say node 1 for now. And then we're going to say node parent left is equal to node 2. Okay. So, I'm not so comfortable with this, but we'll see what happens. So we say node right equals node 1. And is this how it typically is? I feel like, let's see. Weight, x is weight plus y is weight, insert p into L. I feel like the node right and left, let me see. I feel like left is usually 0, right is usually 1, right? So let me think. Now that it really matters is just flipping the bits. So now it's just 0, 1 instead of 1, 0, which is perfectly fine. I just have to think about this for a second. So do we normally put... The heavier ones are normally on the right. So here, let me change this to left and right. Left and right. Okay, so now we have the parent left, we have the parent right, we have the parent weight. What else do we need with these guys? We need the parent character, but the parent doesn't have a character. Left is usually 1. Yeah, okay. Good, I just flipped it around. Thanks, Gusterman. Okay, so now what do we need to do next? Node parent weight. So we have the weights. The parent doesn't have a character because it's an internal node, which is kind of interesting. So we'll see how this goes. So let's go ahead and write this. So this will do that. Now what we need to do is insert this guy back into the initial nodes. So what we're going to say is initial nodes dot push, and we want to push I guess initial nodes or node parent. Is that fair? Let me see. Initial nodes push new node keys. Is it new node parent? Let me go to the end and let's see if this compiles. So we're going to do g++ Huffman. Let me see. No match for operator equals candidate constant expression operator types node and constant value aka node constant. Node equals initial nodes dot top. So do I have to say constant node here? And then I need to change this to node parent down there. Oh, my bad. Node star. Huffman.cvp. Okay, this one looks a little bit cleaner. So let's go ahead and clear a couple times. And let's go up to g++ Huffman. So it says error uninitialized constant node 2. Okay. Let's go here. Oop, sorry about that. I don't need the const. What do you mean I don't need the const? Construct node has no user provided default constructor. Struct node. You don't need the const to... that wasn't the problem. The problem was the equal sign. Let me see. Okay, invalid conversion type constant node to node. Yeah, that's what I thought. So I needed an additional guy there. Okay, let me see. Okay, well that worked. Thanks. So let's do this and do node parent. And yeah, I thought I needed to do that at the start, but I kind of neglected to do so. So now we're going to do a.out. First bit still works. Okay, so now what do we need to do? So I think, unless I'm sorely mistaken here, this should work okay. So this would basically be us removing or adding all the weights together. So what I want to do is at the very end, I want to do the following. Actually, yes. So I want to return. And what do I want to return? I want to return the top. So we want to return initial nodes dot top. Let's see if that compiles. G++. Okay, Then I just want to output whatever I have there. So let's go up here and let's try that. So this guy is going to be removed for now. And we're going to say, oops, sorry about that. We're going to say the following. We're going to say node star, and what do we want to call it? We want to call it root is going to be equal to Huffman of the following initial nodes. Okay, let's see what happens here. So we're going to do std cout, and I want to do root wait. If I can spell anything. Okay, n. Now let's go over here and let's do g++. Runs. Segmentation fault. Fantastic. Okay, good. The pointer only applies the first element. Okay, so let's go down here and let's see where we're breaking. So while initial, so node. Okay, whatever. While initial nodes dot size is greater than 1. So we're going to say std cout initial nodes dot size. Okay, end line. Gonna go to g++, a dot out. Segmentation fault. Okay, good. Let's see out something here. Initialized nodes. 1 second. No, it's not. It's initialized right here. Node parent. I think. Unless there's something wrong with that initialization, which is fair enough. So nodes are clearly being initialized correctly. Okay, so no, we add the two nodes together. Top. Oh, I didn't realize that. Okay, so just above node wait. Okay, so let's go here. Okay. So we're going to say node parent equals new node. Now we're going to do g++, a dot out, 3, 2, 1, 7. Good, that should be right because it's 5, 7. Okay, good. So this is actually doing what we expect it to do. Now what we need to do is recreate the tree, which is kind of a pain, but we'll see how we can do it. So let's go down onto the next function, and we'll see if we can do this. So create bits. Okay, so this is where we need to recreate the tree. It's going to be a vector of Huffman CP, which is something we defined yesterday. Let me go up to the top, and I didn't mean to put the exclamation mark, but that's okay. We're going to write this Huffman CP. Okay. I'm actually going to put this using under this struct because I should probably put it under all structs if it's under two structs. Let's go here. Okay. Okay, so what are we going to do? Huffman CP, 32 arbitrarily set, bit set 128 code. Okay, so we have a length and we have the code itself. That's fine. Let's go down here to the bottom. So basically the idea here is we're setting a length and we're setting a, what are we calling it? We're setting a length and setting a actual code. So here we're going to say, actually, let's do it here. Sets length and code itself. Okay, so we're going to do something super simple then. And what do we need to do? We need to go through and I guess just do it. So we have a node that points to a couple of different things, and let's see what we can do here. So the next is going to be create bits. And let's go up here to main and put that into the function. SDC out root wait, seems fine to me. Now we're going to say, what do we need to return? So we need a vector of Huffman CP. And of course, we're going to need an STD at the start. Okay, vector of Huffman CP. And we're going to call it, let's say, encoded strings, or we'll just say, what do we want? Encoded, encode, did, words. There we go. That makes sense. And it's going to be equal to, what do we want? Create bits. And we want a node star. Oh, sorry. We want root. Okay, let's go up here and change this to what we have, which is node star. And let's see what happens. Everything's changed tremendously. So node star. Okay, and let's also change this to root just to keep consistency. Okay, so where's tree? Binary tree, root. Write this, go down to the bottom. Okay, so now we've read in root. What do we need to do? Well, we start with root, and then we just go along the tree. So now we have to transverse the tree to create bits. Okay. What was I going to do with encode again? See vector Huffman bit strings. Oh, that's going to actually return the string in the end. That's fair enough. Okay. So we have our code. I guess we'd also need the string itself, wouldn't we? Okay, anyway. Transverse the tree to create bits. Let's go down here. So first, we have the node star. And so we'll say, we need to go through all the trees. So we have left and right, right? First, let me try something. STD, cout. What do I want? I want to see out root pointing to the left. Because I know there's something to the left. And then pointing to wait. And let me see what happens if we do this. End line. Got a feeling this isn't going to work out. Yeah, that's what I thought. Okay, let's see. What do we have? Error backtrace. Oh, wait. It does point what we want. Let's go here and let's return invalid pointer. But it does return a 3. Let's not do this here in the Huffman CP guy. Let's go up here and do this in main. So we're going to remove this guy. We're going to say std cout root pointing to left pointing to wait. Then we want to end line. So g++, a.out. See, this one works. That's great. Fantastic. Okay. So this is actually doing what we want it to do. Good. Okay, I was super worried. So let me see. Let's leave that in. Why not? G. Okay, this is really cool, guys. I'm really happy this is working. So let's go ahead and do this, and let's create vector of Huffman CP. And we're going to say vector of Huffman CP. What do we want? We want to call it, I don't know, I don't like the word encoded words. That seems kind of weird because it seems like we've already encoded the words. So let's say Huffman CP, and we're going to call it bit strings maybe? And let me think. So I just realized the Huffman CP guy also probably should have the letter associated with it. So let's go here, Huffman CP bit strings, and let's go up to the top and let's change the Huffman CP guy to also have a character in it. What should we call the character? The character is going to be called key, just to keep it consistent. Encode, let's go down here and let's change it to, what did I call it? Bit strings. Should be fine. So let's go up to main and bit strings. Okay, I think we might be able to get pretty much done with this. by the end of today, which is fantastic. I was honestly, what I mean to say is, even though we got sidetracked doing things that I didn't understand, I think we're now on track, and we can actually finish things by the end of today, and I'm pretty excited about that. So let's go down to bit strings. We have to figure out one more thing, and then we should be okay. So we're going to do return bit strings. Okay, write this. Now let's see what happens if we do g++. Bit strings is not declared in the scope. Bit strings. Huffman CP. Oh, that's because I forgot an std. Let's go over here, g++, a.out. Good, okay, writes just fine. So now we have a thing that I'm not sure if I can fully, if I fully know how to go through. So we need to traverse the entire tree. So basically we need to go left and right at every iteration. So we'll go left and look at the weight. We'll go right and look at the weight. And then we just keep going down until we're out. Okay, so let's see how we need to do this. We need some sort of while loop. No, that doesn't make any sense. So we need to go through all the different nodes, right? So we have a left node, we have a right node, we also have a parent node, which is fine. Okay. So, let's remove this line. What happens? Can we? I'm gonna try something. std cout. And let me check something. Let me say node or root pointing to left, pointing to left, pointing to weight, end line. This should have a weight of 1, I think. Oh no, that has segmentation fault. Let's do, oops, sorry about that, dd. One second. This isn't gonna work. No, I didn't think so. Okay, that's fine. So breadth or depth first searches. Okay, well, let's see. Breadth first searches. Breadth first search is an algorithm for traversing searching trees. Okay, fair enough. This is what we need to do. So breadth, or you said the other one was depth first. So what's the difference then? Breadth first search is an algorithm for traversing or searching tree or graph data structures. It starts at the tree root node and explores the neighbor nodes first before moving on to the next level neighbors. Okay. It was invented in the late 1950s by E.F. Moore, who used it to find the shortest path out of a maze. Fair enough. And discovered independently by C.Y. Lee. Okay, input, graph, that's fine. Breadth first search, for each node in graph, n equals distance equals infinity, n dot parent equals nil. Create empty QQ, root distance equals 0. Did I say transverse? Oh, my bad. I didn't mean to. Did I write that in the code too? I bet you I did. Traverse. You're right. My bad. What does transverse mean? One second. Oh. Situated. They're actually very close in... Okay, that's fine. And then you said the next one is depth. First. Search. Okay. What do we have here? Procedure. Label V as discovered. I think the other guy looks a little bit easier to put in. So what do? We do for each node in n in graph. n.distance equals infinity. n.parent equals nil. Okay. Create empty QQ. And then we say root.distance equals 0. Okay. Q.inQ root. While Q is not empty, current equals Q.dq. For each node n that is adjacent to current, if n equals distance, n dot distance equals infinity, n dot distance equals current dot distance 1. Is it really? Let me see. Procedure, DFS iterative. Let S be a stack. I already am not following. S dot push V. While S is not empty, V equals S dot pop. If V is not labeled as discovered, label V as discovered. For all edges from V to W in G dot adjacent edges do... What's the idea? Let's see. An algorithm for traversing the searching tree or graph data structures. The following graph. Okay, so what do we need to do? We need to go through... I'm sorry, transversing is a word I hear more often than traversing, so it happens. I don't know why, but I've definitely heard transverse more than traverse. They're different words, I know, but I think because I do physics, transverse is heard a lot, so sorry about that. Okay. What do we do? So I just need to... Maybe this will help? Nope. Okay, data structures and depth first. Traversal. Top S stack. Let me see. Only unvisited adjacent node is from D to C now. What? Okay, initialize the stack. Mark S as a visited and output it on the stack. Okay. Explore any unvisited adjacent node from S. We have 3 nodes and we pick any of them. For this example, we shall take the node in alphabetical order. Mark A as visited and put it onto the stack. Explore any unvisited adjacent nodes from A. Both S and D are adjacent to A, but we are concerned for unvisited nodes only. Okay. Visit D. Choose B. Okay, let me just think about this. Okay, so what we need to do is go through all of these guys, right? So what we can do is we can go through. We started the root node. And I guess what we can do is we can add in a parameter up top. Let's add it in and say, what do we want? Node default. So we want... in the node itself, we can add something in, and we can add in visited. So we'll say bool visited equals false. Okay. Quick G++. Okay, that seems to work. A.out, everything seems to be fine. Good. Let's go down to the bottom. So what do we need to do? Well, what we're gonna do... I don't like this idea. It doesn't make sense. Okay. What else do we need to do? What else could we do? Okay, all we have to do is traverse the tree, right? So we start at the root node. We go left to right, right? We can only go left to right. So we choose to go left or right. I don't know what you mean by cycles. So, okay, so we can go left to right. Basically, we need a way to tell if a node does not have a left or right, right? That's the thing we need to be able to tell, right? So if we can tell that, we're fine. So how do we need to do this? We'll say, what is a cycle? Is that like when you go in a circle? Okay, that's fine. So let's go down here, return bit strings. Let me think. We can go left or right. Here, let's draw this out. Page, new page before. Okay. So we can go left or right. So we're at some sort of root node. Okay, we can go either to the left or to the right. We have some guy here, and I'm assuming it looks something like this. Because we only have 1, 2, 3. Oh, maybe we have 4. So maybe it looks something like this. That's fine. Okay, so we can go left to right, and then here we can go left to right. But we need to do all options until we're out. The thing is, I don't know how to know if we're out, right? That's the thing I need to figure out. If I could figure that out, everything would be super simple. So, like, for example, if I call node 1, let's say 1, that's a 1, pointing to left, it's just going to give me an invalid pointer. I need to figure out how to say that it doesn't have a node on the left, you know? And that's the thing I don't know how to do. So outside of that, all we need to do is go left to right, and then go left to right again. And then we just need to keep going left to right until all of them have gone both left and right. And that's all we need to do. Okay, so let me see if I can find a way to tell that, and then we can go from there. Because even the searching things that we were looking at, they required you to know what is left and what is right. Like what is, like if there is any data in the left or right, and that's what I can't figure out. So, if node left, let me see if that works. So here's what we're gonna do. If let me do root. Let's do root left, left. Okay. Oh shoot. Undo. Print. Oh, what am I doing? std cout exists. And line. Let's do g++, get it out. Okay, so now let's try this. G++, a dot out. Okay, so this seems fine then. So let's go. Now let's go ahead and write it. So what do we need to do? We're going to say, this is going to be super inefficient. I get that. So we'll say while, what do we want? Where you have the node constructor with the key and weight, do left equals right equals parent equals null pointer. Where you have the node constructor with the key and the weight, do left equals right equals parent equals null pointer. What? Okay. That's not going to compile. Let's go up here. So you're saying while we, let me see. Oh, when we do the initialization, I see what you're saying. So we do initial nodes, and here what we say is, lolly lol 1975, the traversal tree must be a recursive algorithm. Yep, that's fine. I'm working on that. Okay. So what do we do here? We're going to say initial nodes push back, new node keys. And depth first. Let me see. So we're going to say let me see. So we're going to do initial nodes dot push. But what I actually want to do is this. So let's do temp node. So we're going to say new. We're going to say temp node equals new node with keys and weights. And now we're going to say temp node pointing to the left equals null pointer. Temp node pointing to the right equals null pointer. And now we're going to say temp node pointing to parent equals null pointer. Okay, so now when we go down here, let's see, we're going to do push back temp node. Or just push. Okay, let's write this, go over here, G++. Okay, that's because this node doesn't have a star. Okay, G++, A dot out. Okay, this one seems to work just fine. That's why I suggested it as well. Yeah, I don't know. It seems more complicated to me. Of course, that could be because I don't know what a stack is. So this is my bad computer science coming out. Here, let's see what they have. So they have, okay, let's see what we have. So struct vertex, that's fine. Int stack max, array of vertices, vertex, adjacent matrix max max, vertex count equals 0, push. Okay. Let me see. Breadth first is pretty useful. If you wouldn't generate the character code pairs, would do a lookup every time. Okay, let me see. So they have down here, while is stack empty. So while that's true, that's fine. Then we're gonna say int unvisited vertex is get adjacent unvisited vertex peak. Okay, so now we say if unvisited vertex equals -1 pop, else list vertices visited equals true. And display vertex push unvisited vertex. Let me see. So int unvisited vertex equals get adjacent unvisited vertex peak. If unvisited vertex equals -1, we pop. Since the Huffman tree naturally has higher probabilities closer to the root, you'll find your code point faster with BFS. But I thought you guys said to do DFS? What am I doing? One second. Depth first. Breadth first. Because breadth first seemed to make more sense to me. Well, I mean, this tree is small. I mean, future trees could be quite large. Okay. For each node in n in graph, n.distance equals infinity. Yeah, see, this one makes more sense to me than the other one. Like, I can at least read this code. The other one I can't figure out at all. Okay, create empty queue, q, root.distance equals 0. Okay. Current equals q.dq. Okay. For each node n that is adjacent to current. Is it harder to write? Because it looks so much easier. Like, this makes sense to me. This one doesn't. Let me see. Breadth first search. Ugh. First search. I don't know. Okay. For each node n in graph, n.distance. So I guess the for each node would be hard to write. Because we can't go through n. Okay, so that's... I'm not sure. Well, in all of the stuff I'm looking at, DFS looks way more difficult. It looks super difficult when compared to this one. This one's just like 20 lines of code. All of this stuff looks huge and freaking annoying. So like this, I don't even know what this is saying. So label V as discovered, okay? For all edges in V to W in G.adjacent edges do, if vertex W is not labeled as discovered, then recursively call DFS. So what we're doing is we're saying for all edges, Okay, so what is G? So G is the graph, V is the vertex. So we can only read in root. Label V as discovered. For all edges from V to W in G dot adjacent edges V, do for all edges from V to W. Label V as discovered. What is W? Void root. If root left, DFS is root left. If root right, DFS do stuff for the current node. You know what, guys? I think I'm just going to do this on my own. I can't, right now, I can't figure this out. Again, to be totally and completely honest, I hardly ever use pointers in C++ code. So it's not something... Yeah, I'm not sure I fully... I'm going to have to look into this. DFS for trees. Let me see. Tree transversal depth first search. Even more complicated. Dagnabbit. Okay, I'm just gonna make one up. I'm not gonna worry about this. It doesn't make sense to worry about that. And I'm gonna do this on my own time. So I'm not gonna worry about it here. At this point, guys, I think I'm just gonna go ahead and write this. Yeah, I just found the link and it doesn't help. It's just like, yeah, I was just there, I think. Let me see. Open link. Yeah. Yeah. That's just, I don't know. This whole thing is rather complicated. And it's just because, again, I don't ever use trees and I never use pointers. So when you put them together, it's stuff that I've never seen before. Sorry about that, guys. But I think what I'm going to do is I'm going to go ahead and commit what we have to GitHub. And I'm going to leave this here. So what we need to do is set length and code itself. Let's add a quick note. To be continued. And we'll get this done tomorrow morning. Right and quit. So let's go ahead and do git commit Huffman.cpp. So git add Huffman.cpp. And now we're going to do git commit. And we're going to say added skeleton for, simple Huffman algorithm. We need to, what do we need to do? Traverse the tree, and recreate, and create the appropriate bit strings. Okay. Git push, origin, master. Okay. And at that point, guys, it's 6:59. I realize I started a minute late, and I'll probably end a minute early. So sorry about that, guys. But we're getting there. I'm content with how far we got today. We didn't quite get all the way through, and that's just because it was implemented a drastically different way than I thought it was going to be implemented. So because of that, I need to now learn some new stuff to figure out how to do this. It's probably for the better to do this since I just don't know anything about trees or anything like that. So this is probably good. I'll look into this sometime during the day, probably over lunch, and see what we need to do from there. Yes. So at this point, guys, I think I'm gonna go ahead and end the stream, and then we'll work on this a little bit afterwards. Let me see. Loyal 1975. Our node is defined by struct node. Yep. Node left. Node right. Yep. Let me think. Okay, so anyway, guys, I'm gonna go ahead and end the stream. Have a fantastic day, night, evening, afternoon, morning, whatever time it happens to be your time. And I will see you around next time for the next episode of Simulators when we finish the simple Huffman tree, which should have been done yesterday, but that's okay. Things take a little bit longer. And that's okay. Anyway, guys, I'll see you around. Have a great day. Bye, guys.